paper 333.
If you can give me a couple of minutes, I'm taking a
Yeah.
look at it right now. Yeah.
I shared the program in the text. In the text, you can check the program.
Yeah. So this is the session 3, right? The paper IDs are 1956, 225, 265, 296, right?
This section should be section 2.
Session 2. Okay.
Yes.
2387, 256, 274, 333, 410, and 454. And the timing for it is like 15 minutes each, right? For the session. Is that a fair statement?
Due to time restriction, 10 or 12 minutes is enough, and for the 3 minutes for the questions and answers, I offer you.
Okay. Sounds great. Then we can get started. So
Okay.
the first paper would be paper 23, right? I would request the presenters to initiate it as soon as you can.
Yes, sir.
Thank you.
Can you see my screen?
Yes, we can see your screen.
Okay. Good morning, everyone. My name is Chaoyue Huang from Shanghai University. Today, I'm pleased to present our work titled Information Asymmetry Game for Trigger-Based DNA Model Watermarking. In this work, we studied the robustness of trigger-based model watermarking against removal attacks. In particular, we model the interaction between the model owner and the attacker using a game theoretic framework within information asymmetry. This framework allows us to analyze the strategic behavior of both sides and derive theoretic insights into watermark robustness. As we see, deep neural networks have achieved remarkable success in many domains, such as computer vision, speech recognition, and natural language processing. However, training high-performance models usually requires large data sets and expensive computational resources. As a result, trained models become valuable intellectual property assets. Therefore, protecting the ownership of these models has become an increasingly important problem. One promising solution is model watermarking, which embeds hidden ownership information into the model so that the owner can later verify the copyright of the model. Among various watermarking techniques, trigger-based watermarking has become a widely used approach. The basic idea is to construct a small set of trigger symbols that contain a specific pattern. During training, the model is trained on both the clean datasets and the trigger dataset. After training, the watermarked model behaves normally on clean inputs, while trigger inputs will produce a predefined output label. This special behavior allows the model owner to verify ownership using black box queries without accessing the internal parameters of the model. Although watermarking provides a way to protect model ownership, it is still vulnerable to removal attacks. An attacker may try to invalidate the watermark while keeping the model usable. Several removal strategies have been proposed, including pruning, fine-tuning, knowledge distillation. In general, the attacker aims to maintain the model's classification accuracy while significantly reducing the watermark success rate. One widely studied removal attacking is pruning. The key intuition is that watermark information is often stored in a relatively small subset of neutrons. By removing these neutrons, the attacker may weaken the watermark response. The desired attack outcome is that the model accuracy remains almost unchanged, while the watermark success rate is significantly reduced. This creates a fundamental trade-off between model utility and watermark robustness. So to better understand this adversary interaction, we propose to model the problem using game theory. In our framework, there are two players. The first player is the defender, who embeds the watermark during training. The second player is the attacker, who attempts to remove the watermark after the model is released. A key characteristic of this interaction is information asymmetry. The defender knows the secret trigger and watermark configuration, while the attacker only observes the released model and must infer the watermark indirectly. In our game model, the defender strategy is represented by three parameters. The first is the watermark sparsity, which controls how many neutrons carry watermark information. The second is trigger complexity, which affects the difficulty for attackers to infer the trigger. The third is watermark strength, which reflects the ratio of watermark symbols used during training. The attacker strategy includes the pruning baggage, the number of estimation iterations, and the exploration factor controlling randomness during neutron selection. Based on this formulation, we derived a theoretic model describing how the watermark success rate changes after pruning. Our analysis shows that the watermark success rate decreases approximately exponentially with the pruning baggage. Furthermore, by analyzing the attacker's utility function, we derive a closed-form solution for the optimal pruning baggage. This optimal point represents the attacker's best strategy under the trade-off between watermark removal, effectiveness, and pruning cost. So to validate our theoretical analysis, we conduct experiments on the CIFAR-10 dataset. The base model is a ResNet 18 trained from scratch. We apply a bad night style trigger patch with a size of 5 by 5 pixels. The trigger is inserted into 1% of the training samples. After the watermark embedding, the model achieves around 79% accuracy and approximately 90% watermark success rate. As you can see in the figure, this figure shows the model performance under different pruning baggage. We observe that the classification accuracy remains almost unchanged, even when several percent of neutrons are pruned. However, the watermark success rate gradually decreases as the pruning baggage increases. This behavior is consistent with our theoretic prediction of exponential watermark decay. So from the experimental results, we can draw several observations. First, watermark information is indeed sparsely distributed in the network. Second, the exponential decay model fits the empirical data very well. Finally, the theoretically predicted optimum pruning baggage closely matches the empirical optima observed in experiments. These results confirm the effectiveness of our analytic framework. In conclusion, we propose a game theoretic framework for analyzing trigger-based model, watermarking under proving attacks. Our model captures the strategic interaction between defenders and attackers under information asymmetry. Both theoretical analysis and experimental results demonstrate the effectiveness of the proposed approach. In future work, we plan to extend this framework to dynamic game settings and explore our watermark removal strategies. Thank you for your attention. If you have any suggestions, please contact us by this email. That's over. Thank you.
Thank you. The floor is open for questions now. Yeah, thank you so much. We appreciate it. We'll be going ahead for the next paper unless anyone else has any other questions. All right, I'll take it as a no. Thank you so much. Thank you once again for the presentation.
Thank you, sir.
Okay, the next presentation is the paper 87.
Yeah, is it audible?
Yeah, you're audible.
You are audible.
Yes, sir. I'll share my screen now.
Sure.
Good morning. My name is Anirudh GP. I'm from the Department of Electrical Engineering at PS University, Bangalore. I'm presenting joint work with Anantraj Rao and Ashwin Thomas and our faculty advisor, Dr. Srinivasa V.S. Sarma, sir. And our title is our paper title is Design and Analysis of Energy Efficient ASCON ATPQ. Submitted to the IEEE 14th International Symposium on Digital Forensics and Security. Let me briefly walk you through the structure of the presentation. We begin with the introduction and motivation, why post-quantum lightweight cryptography matters for IoT. and we cover the relevant literature and research gaps we identified. Following that, we'll discuss the algorithm specification, specifically the difference between ASCON ATPQ and the widely discussed ASCON 128. Then we described three different hardware implementation approaches. The bulk of our results covers FPGA and FPGA evaluation and ASIC synthesis results and impact of clock gating. And the final thing will conclude with the conclusion and future direction. Introduction and motivation. The motivation for this stems from a convergence of three trends. The first thing is IoT explosion. Billions of resource-constrained embedded devices are being deployed globally. These devices require cryptographic security, but traditional heavyweight algorithms like AES are simply not feasible for power and area budget of these platforms. NIST responded this by standardizing ASCON as lightweight cryptography standard, chosen for its power efficiency and suitable for embedded application. Second, the quantum threat. The Grover's algorithm, when applied for symmetric cryptography, effectively halves the security level in terms of bit length. This means 128 key sized algorithm, classical security algorithm, would actually effective bits would be 64 for post quantum security. For many applications, 64-bit is no longer considered adequate. This brings us to the ASCON ATPQ. The solution which it provides is by increasing the key size from 128 to 160 bits, restoring the 80-bit post quantum for our post-quantum security. The literature survey, the literature review which we done was prior hardware work on ASCON almost excluded the ASCON one, included the only ASCON 128 variant. In many of the researchers only focused on ASCON 128 and benchmarked in the FPGA, and we can see plenty of research done on this. But ASCON, however, the ASCON ATPQ presents the research was not done. So comparing our work directly responds to the call by delivering the first unified and unified FPGA and ASIC evaluation of ASCON ATPQ, providing a coherent baseline against well-studied ASCON 128. Coming to the algorithm specification, comparing the two variants, ASCON 128 and ATPQ share the same classical security level of 128 bits. They also share the same rate of 164-bit, the same capacity also of 256 bits, and same round configuration of 12 initialization and 6 block permutation rounds. The sole structural difference is the key size, increased from 128-bit to 168-bit in ASCON ATPQ. This is what delivers improved post-quantum security, 80 bits effective against Grover algorithm compared to 128. Regarding the permutation structure, each round consists of 3 layers: the round constant, and round constant. The overall AED follows the Spotch duplex construction, initialization, loads, key, and nonce 120 rounds. The associated data is absorbed. With 6-round permutation per block, plain text, and XORed with the rate and reduce to produce the ciphertext. Finalization reinjects key and applies another 12 rounds, and finally 128-bit authenticated tag is extracted. Now coming to hardware implementation, we implemented the ASCON ATPQ using 3 distinct design approaches, which allows us to decouple algorithmic overhead over microarchitecture optimization. The first in HLS-based 128 implementation using Vitis HLS. This serves as baseline reference. It is a synthesis of C and C++ description into sequential and non-pipelined architecture, closely following the algorithm specification. It target on RTX 7 and Zinc 7000. The second HLS-based ASCON 128 ASCON ATPQ, a functional prototype, without algorithm level hardware optimization. The established HLS baseline for ASCON ATPQ, the same FPGA targets a nominal 100 megahertz clock. The third, our primary contribution, in-hand optimized Verilog RTL optimization implementation of ASCON 128, ASCON ATPQ. This uses a clock accurate iterative FSM. This executes one permutation round per clock cycle. It incorporates register level clock gating and dynamic power reduction. Yes. Coming to the results which we got was from FPGA. The FPGA achieves 2.2 times reduction in LUT count versus the 128 baseline, and 1.85 times improvement to throughput and lowest power consumption on both platforms. This is the key takeaway from this thing. Coming to the ASIC result and clock gating impact, what we found out was, in terms of the takeaway was, clock gating is highly effective and low cost technique for dynamic power reduction in both designs of ASCON ATPQ, demonstrate superior area efficiency in raw throughput across basic and gated configurations. This is the comparative analysis across platform. To summarize the cross-platform comparison, in throughput, ASCON ATPQ consistently outperforms ASCON 128. The Vivado implementation achieves 1.85 and 1.89 times improvement on FPGA, and the ASIC basic configuration achieves 2.71 times improvement. Even the gated configuration of ASIC maintains 1.1 times advantage. In area, ASCON 128 ATPQ uses 2.2 times fewer LUTs on both Arctic 7 and Zinc 7000, and 1.9 to 2.1 times fewer cells on ASIC. This particularly is a significant finding because ASCON ATPQ uses a longer key, yet requires substantially less hardware area, and this constitutes the results in purely entirely in RTL level optimization. The handcrafted FSM eliminates the overhead accumulating during HLS compilation. These are the conclusions. First, it delivers the first comprehensive unified FPGA and ASIC hardware evaluation of ASCON ATPQ, establishing baseline for the community. Second, the Verilog RTL achieves 1.9 times cell reduction relatively to ASCON 128. Third, the clock gating is shown to be highly effective, reducing dynamic power by 2.7 to 6.9 times across evaluated designs, with the clock gated ATPQ reaching 0.68 picojoules per bit. Fourth, we established clear distinction between RTL and HLS designs, observed performance gains. Fifth, ASCON ATPQ is demonstrated by strong candidate for post-quantum constraint IoT deployments. It is 160-bit, provides 80-bit effective to post-quantum. It does so with superior area throughput and energy efficient compared to ASCON 128. These are the references which we have used. Thank you.
Thank you. Thank you, Anirudh. The floor is now open for any questions. It's going twice. Anirudh, thank you so much. We appreciate your presentation. Thank you so much.
Thank you, sir.
The next paper is paper ID 256. Your voice is very faint. I would appreciate if you can. Yeah.
So right now?
It's not that great.
So now,
Yeah, much better. Yes.
yes. Yes, just
Okay.
yes.
And you're Vishruth. Okay. Would you
Yes.
want to share your presentation, please?
Yes, sir. So is my screen visible?
We can see your Zoom.
So right now?
Yeah.
Yes, sir. That should. Yeah. Good morning.
Is there any way you can make it like a full? Yeah. Thank you so much.
Yes. Yeah. Good morning, everyone. Myself, Vishruth. I'm a final year BTech student in PS University, which is located in Bangalore. And our paper is comprehensive review and experimental study of holiday-aware multimodal crime prediction. So what we are trying to tell through our paper is that can holiday be considered as an external factor for crime prediction? So if we take crime prediction, what major thing which comes to our mind is we collect crime data for like past 20 years and we put a trend. And based on the trend, we try to predict like which type of crime may happen or which type of crime has the most possibility to occur in the coming future. But some people have tried to improve it. Some people have used sentiment from social media platform and correlating it with the crimes in the past years. They're predicting the future crimes. Some other people have used weather as an external feature for predicting crime. So what, while going through the research paper, what we came to the decision is that what we tried to do in this paper is to see if holiday can be a valid external factor for crime prediction. So based on the research paper, what we read, we came to know some of the research gaps. Many research paper only consider historical data, just the past crimes, and like they didn't consider any external factors like holiday, weather, or anything like that. And some of the people who have used sentiment analysis of social media platform didn't consider slang or sarcasm. They just use some basic sentiment analysis tools. And traditional models, it's difficult to integrate with the, like if I consider a holiday, but some people use data like crimes which have occurred in the past, but some model have difficulty in correlating them. So we proposed an hybrid workflow for overcoming all these things. So what we do is we collect two sets of data. One is the criminal data. Like if we consider a region like Chicago, we have collected, our data set is based on Chicago from 2000 to 2020. So we found the data set by using some crime portal. What's the name of it? So yeah, for collected for 10 years, 2010 to 2020, we have extracted it using certain keywords and using latitude and longitude. We used twitter.io as a tool for extracting it. So what we are doing is we are collecting Twitter data Twitter data of the region of Chicago for the past 10 years and also the crime data of the same region. And we are doing, so the Twitter data is passed through a sentiment analysis model. What it does, each tweet, it calculates it as positive, negative, or neutral. After doing sentiment analysis, we get sentiment score. That sentiment score is added to the crime data, which you have collected earlier. And that combined output is going to the crime prediction. So the crime prediction part is done by a model called XGBoost regression. It tries to correlate with the crimes, holidays, and sentiment and tries to predict the output. So in our second model, sentiment analysis, this is the approach which we have used. We are combining three models, Affin, Vader, and Robata. So what Affin and Vader does it, they already have some predefined words with some value. So if those values occur in a tweet, they give it like a value like +2, -2, and the score is aggregated in the end. But sometimes that case might not happen. Like some word, it gives a different context in the beginning of the sentence, but a different context at the end of the sentence. So that's where Robata comes into picture. It is a model which is mainly used for sentiment analysis. It does not just see the word, it sees where that word is located in the sentence, and based on that it gives the value. So all the three output go to a ensemble learning model. So the more weightage is given to Robota, but a Robota has a limitation, like it is only as good as the training data which it gets. So if a tweet comes that is outside its training range, it might mispredict. So to consider that issue, we have used Affin and Vader. So a little normalization might come into the picture. So yeah, so the crime prediction model is the XGBoost regressor. So what it does is it mainly has 300 to 400 decision trees. It takes each feature and tries to divide the data set into many partitions. Similarly, each tree divides into certain parts, and the same output is gone to the next tree and the next tree. So the same sequence carries on. This is the Twitter dataset which we have created. The Twitter ID, the text, and this is the historical crime data, the start date, end date, and also due to the limitation, we couldn't get daily crime rates, so we aggregated it into 3 to 4 days. Like Monday to Thursday is one row, and Friday to Sunday is another row. So yeah, this is the crime data set, and this is after pre-processing the crime data set, because we had some other language. Even though we used English as a parameter, we got tweets of some other languages, so we needed to pre-process them. And this is the output which is going to the final crime prediction model: the start date, end date, various types of crimes, the number of crimes, and the holiday, the number of holidays that date interval contains, and the sentiment, which is the output of sentiment analysis. So this goes into the crime prediction model. So for model evaluation, we used 4 type of model for crime prediction. One is the temporal model, which just uses the crime data set. Next model, it uses the basic crimes plus holiday. The third model, the basic holiday plus sentiment. And the fourth is the hybrid one, which includes all the 3. So in order to see if a model is right or wrong, we use 2 evaluation parameters: mean absolute error and R square, and use time series cross validation to preserve the consistency. So yeah, so this is the result which we got for battery. The black line is the actual crime rates, and the dotted blue line is the one which just has the crime, means using crime it has predicted, and the orange one, the crime plus holiday, and the green one, the crime with sentiment, and the red one is the aggregation of all. So this is the assault, criminal sexual assault, criminal damage, and this is the comparison between R4 models. So this can be clearly seen in the next slide. So yeah, this is the MAE, and this is the percentage improvement when compared to the base. So what we can see is the assault gives us a better, the lesser the MAE, the better our model predicts. So assault, in the case of assault, the holiday does better. In case of burglary, our model does better. Criminal sexual assault, it does better. Criminal damage, it does better. And robbery, it remains the same. So, and also the model which has all the features which we are told, it does better in battery, burglary, and criminal sexual assault. So what through this we can tell is, yes, holiday can be used as a major factor in crime prediction, but since there is a bit of randomization, the values will not be exact if you rerun the test, but the pattern is same. So what the improvement we can see, the same thing can be seen if you run the model again. But what we observed is that the crimes which are related to property often predict better when we consider holiday as an external factor. So what we are trying to tell is that, yes, holiday can be used as an external factor in crime prediction, but only in the cases where crimes are related to a property. So future work, what our approach does it just isolates a single city. So multiple city doesn't come into our approach. And we had just considered social media platform like Twitter, but we can merge it with various other sources and even improve our model. Or we can use spatiotemporal modeling for better result, or use many advanced deep learning approaches like LSTM, TCN for capturing even more complex crime patterns. So yes, sir, that's it.
Thank you so much. The ground is open for questions. Going once, going twice. Thank you, Vishrat. Thank you so much for presenting your paper. We appreciate your work.
Yes, sir. Thank you, sir.
The next paper on the agenda, it's paper ID 274. Do we have Mihai? Vasu, I would request you to go on mute, please. Thank you.
No, sir, my paper ID is 410.
Yes. Yeah, I think your paper is like, there are two more papers before yours. So I'll let you know.
Okay, no problem.
Do we have any presenters from paper ID 274? Okay, moving on. Paper ID 233, high accuracy is not enough.
Yeah, hello, can you hear me?
Yes, we can hear you.
Okay, so let me share my screen.
Thank you, Alessandro.
All good, can you see my screen?
Absolutely, yeah.
Okay, so yeah, I am Alessandro Palumbo from Paris-Saclay University. And yes, today I'm going to present our paper demonstrating and showcasing that the high accuracy in machine learning tasks is actually not enough. And if you want to have a look to the preprint here, there is the QR code. I cannot, yeah. So a little bit of introduction. So as we know, AI systems are increasingly deployed in critical decision-making context, but technical performance alone cannot guarantee a legitimate inference, sorry. And the questions are, what happens when a model is accurate but wrongly built? Can a bias exist before or during the data collection? And how do we evaluate what a system should predict? Basically, just to add a little bit more of motivation, legal and criminal justice contexts are now rely on machine learning and on the machine learning algorithm for decision support. And usually, in some digital scenarios, in some digital domains, the accuracy is the dominant evaluation metrics, and the performance evaluation often focuses exclusively on predictive correctness. And as we were saying before, does high accuracy guarantee a legitimate interface? So, in theory, technical performance may not reflect epistemic or normative validity. And of course, there are regulations like the EU AI Act for criminal justice, and the criminal justice is labeled as a high risk because it requires assessment beyond accuracy, of course, like transparency, fairness, and also fundamental rights. The goal of the studies is presenting what should not be done And we try to answer the question, can machine learning models achieve high predictive performance even when the inferred relationships lack epistemic validity and or normative justification? So this paper demonstrates why accuracy alone is not enough, it's insufficient, and why such systems must not be developed, deployed without normative evaluation. And the key contributions are the following. So demonstrating high accuracy, that a high accuracy can conceal epistemic bias. And we show that biases arise at task formulation level. So the problems begin before and data collection in how we define what we want to predict. And we focused and we referred to the Lombrosian criminology as a case of study, and this is a scientifically discredited theory just for demonstrating what the machine learning does not have to do, highlighting, in fact, the limitations of accuracy-driven evaluation. So, what's the Lombrosian theory? So, it's a late 19th century theory elaborated by Professor Cesare Lombroso, and it attempted to establish criminology as an empirical science through biological observation. And he was claiming that criminality is predictable from facial features like facial asymmetry, jaw prominence, cranial shape, and things like this. And this is something which is based on psychognomy and biological determinism. And of course, this is something which has been discredited by the scientific and ethical, because it's ethically problematic, because of course it lacks of causal justification and it uses biased samples, and at the end of the day it's legitimized discrimination. Why we used this framework? Just to make an example and just to illustrate the risk of confusing patterns with meaning, and to show that formal correctness is different from the epistemic legitimacy. And of course, parallel model machine learning based classification, it's something that machine learning has not to do. So doesn't have to do in this example for detecting something, in this case, the criminality. So the pipeline was the following. We asked a GPT model to generate 60 Lombrosian pictures, 60 Lombrosian faces and 60 non-Lombrosian faces. And then, once our dataset was built, we used a ResNet CNN for classification, for training, validation, and for the detection. And again, so just to add some context and some details, we got 120 face images, facial images, and we used 70 for the training, 15 for the validation, and 15 faces for the test. And we got two different categories. So the 30 Lombrosian males and 30 Lombrosian females, and same 30 non-Lombrosian males and 30 non-Lombrosian females. And then we used the ResNet CNN to distinguish and to see if the ResNet was able to detect the criminal looking at those faces, again, following the Lombrosian theory, which is scientific, discredited. And at the end of the day, we got close to a perfect accuracy just after 10 epochs. So we got very great results. But again, the performance measures alignment with construct task, not validity of infrared relationships. And the model actually exploits dataset coherence, not meaningful patterns. And what about implication for the legal AI? So accuracy alone cannot, of course, validate AI systems. So high performance on few tasks does not justify development, the deployment in high stakes context. And we must access the epistemic validity of task formulation, evaluating whatever the predicted predicted relationships are casually justified and normatively acceptable. And of course, we do need normative constraints at the design level. So ethical and legal principles must inform what models are allowed to predict. And in fact, in the EUI Act is something which, I mean, it's written there, so it requires transparency. We do need to respect fundamental rights, assessment, and of course also human oversight beyond technical metrics. And because there are several broader risks, so machine learning may legitimize some discriminatory inferences, and appearance of objective can mask normative choices. Feature biased classification is something which is detached from causality. And again, high accuracy can create false sense of reliability. So in conclusion, we demonstrated with a practical example that high accuracy is different from the epistemic validity, and technical performance does not guarantee that the inferred relationships are meaningful or justified. In addition, biases can be embedded in the task definition itself. In this case, the choice of what to predict was encoding a kind of discriminatory assumptions before any data used. And performance metrics, again, must be complemented by normative evaluation. So that's it. So if you have questions, please feel free to ask, and do not hesitate to reach out. We are very open for collaboration.
Thank you, Alessandro. The floor is now open for any questions. Thank you, Alessandro. That was a good presentation. Thank you so much.
Thanks.
Also, we have the session chair joined. Sandeep, the floor is also yours. And the next paper is paper ID 410. Do we have a representation? Vasu? Vasu, you are on mute.
Hello.
Yes, Vasu.
Sir, can I present?
Yes, please.
Okay, sir. Sir, is my screen visible?
Yes, it's visible.
Okay, sir. Good morning, everyone. My name is Vasuraj Jain, and today I will be presenting my research on artificial intelligence-driven predictive models for identifying risk factors of chronic diseases. Uh, with a focus on diabetes predictions, these this research explores how machine learning and deep learning models can help in early detection of diabetes using clinical data. This presentation is structured into the following sections. First is abstract, second introduction, literature review, methodology, results, conclusion, and references. Here is our abstract. Diabetes is a major global health issue, and early detection is very important to prevent complications. In this study, we use the PIMA Indian diabetes dataset and applied two models: random forest, it's a machine learning model, and LSTM, it's a deep learning model. Highlight result confidently. Random forest achieved 97.54% accuracy, while LSTM performed even better with 98.85% accuracy and 98.20% F1 score. Our models outperform traditional methods like naive Bayes, SVM, and even advanced models like CNN, LSTM, and DMO. This shows that combining machine learning and deep learning techniques can significantly improve healthcare predictions. Here is our introduction. In this, we discuss about chronic disease like diabetes affect people globally and require early detection. Diabetes mainly has two types. Type 1 require insulin. Second one is type 2 can be managed with medicines. Traditionally, diagnosis depends on symptoms which may not capture long-term risk. In this important point is this: with this rise of electronic medical records, we can now use machine learning to detect hidden patterns and predict diseases early. This helps doctor make better and faster decisions. Here is a literature review. This table summarizes previous researches in chronic disease predictions. Most earlier models like decision tree and naive Bayes has lower accuracy. Recent study using deep learning improved performance but still had limitation in accuracy and scalability. So our work focus on improving both accuracy and reliability using advanced models. Here is our methodology. Our system follows the structured workflow of diabetes prediction. First is data collection. We use the PIMA Indian diabetes dataset from Kaggle. Then we do data pre-processing. In data pre-processing, we clean the data by removing missing values and outliers and selected important features. Then we do data normalization. We applied min-max normalization to scale the data. Then we do data splitting. We divide data into training and testing sets. Then we do data balancing. We use smooth to handle class imbalance. In this, the step is crucial because imbalanced data can reduce model performance. Then we do model deployment. We use two models, random forest and LST. Then we evaluate some metrics. We evaluate using accuracy, precision, recall, F1 score. Here is result and discussion. This slide shows the confusion metrics of both the models. And in table 2, you can see the proposed model performance on the data set of PIMA dataset. As you can see clearly, our LSTM performed very well on the dataset. LSTM achieved 98.85% accuracy, precision is 98.51%, recall is 98.78%, and F1 score is 98.20%, and random forest achieved 97.54%, precision is 96.40, recall is 98.223, and F1 score is 96.32. Like random forest perform well but has more classifications error. LS team perform better with one false positive and one false negative, showing higher accuracy and reliability. As you can see this thing in confusion matrix. This means LSTM is more effective in correctly predicting diabetic and non-diabetic patients. Here we analyze LSTM performance. Training accuracy crosses 90% quickly and improves stability. Training and testing curves overlaps, showing good generalization. The loss graph shows continuous decreases, meaning the model is learning well and not overfitting. Then the model comparison table. In this table, we compare different models. Like traditionally, models have achieving 72 to 79% accuracy. Deep learning models achieve 80 above 89%. Random forest achieve 97.54% and LSTM achieve 98.85%. LSTM achieve best accuracy of all the models. This clearly provides that our proposed model outperform existing approaches. Here is conclusion and future work. In conclusion, early detection of diabetes is essential. Our study showed that random forest provide high accuracy. LSTM provides even better performance with minimum errors. LSTM is more accurate, scalable, and reliable for clinical decision support. In future work, these models can extend to our other chronic diseases, real-time healthcare system integration with mobile or hospital systems. Here is references. There are the references used in this research. Thank you for your attention. I will happy to answer any questions.
Thank you, Vasu. Any other questions from the floor? Going once, going twice. Thank you so much, Vasu. We appreciate it.
Thank you, sir.
Thank you. Now the last paper we have, the real-time vision-based human-robot interaction framework for low-cost embedded robotic arms. Do we have someone?
Yes, I'm here.
Yeah, thank you.
Hope you guys can see my screen.
Yes, we do.
Okay. Good morning, everyone. My name is Anjana Dev. I'm an undergraduate of Informatics Institute of Technology affiliated with the University of Westminster, UK. So today I'm going to present my work on real-time vision-based human-robot interaction framework for low-cost embedded robotic arms. So this work is focused on enabling robots to learn directly from human demonstration using computer vision. So without any further ado, let's dive into the introduction itself. So from this chart, from this slide, you can see there's two charts. So from the first chart, you guys can see about 90% of the large, small, medium in the global enterprises, 90% of the small, medium enterprises are there. So only 10% are large enterprises. 90% of the enterprises in the world are small, medium enterprises. Only 10% are large enterprises. But if you look into this chart over here, from all the large enterprises, 70% of the large enterprises have already adapted to Industrial 4 revolution. But only 30% of the small and medium enterprises have adapted to the Industrial 4 revolution. So we can see there's a clear gap here. Even though 90% of the global enterprises are small medium enterprises, only 30% of them has adapted to industrial automation. So let's see what is the problem that is the small medium enterprises are facing while the backend up when adapting to industrial 4 revolution. So let's dive into the problem. So as you guys can see, the first problem is the hardware cost. Robotic arms and advanced sensors are expensive and require high performance computing. And the second problem, integration and deployment. Systems rely on inverse kinematics and require trajectory planning and making them complex and time consuming to set up. And the third problem is training and expertise. These systems require specialized programming and skilled engineers. So as a result, small medium enterprises are struggling to adapt because of the situations. So from this project, we are hoping to tackle two problems, which is the integration and deployment problem and the training and expertise problem. So let's see what is the solution we are proposing. So to address these challenges, we propose a vision-based learning system. The robot learns tasks directly from human demonstration using a camera. Human motion is captured using pose estimation and converted into robot joint angles and refined using Kalman filter for smooth executions. The entire system runs on low-cost ESP32 microcontroller embedded platform. So by using this ESP32 microcontroller, we are making sure that the entire system is wireless. That's what the small and medium enterprises want. They want to make the system simple as possible. So to make it simple, we are making use, there are no wires in the factory, there are no wires to plug there, the user doesn't have to carry the laptop everywhere. So the entire system is wireless. So the user can deploy it easily as possible. So as you guys can see, we are tackling two problems here. The first problem is integration and deployment cost. The second problem is training and expertise cost. These are the two problems we are going to solve with the small medium enterprises. So they would have a fighting chance against the large enterprises. Okay. So this is the system architecture. So the system diagram, this is the pipeline. First, human motion is captured using a camera and processed using pose estimation. Then joint angles are computed from key points. These values are smoothed using Kalman filter to reduce noise. Finally, the process signals are sent to the ESP32 microcontroller, which drives the robotic arm in real time. The system also supports motion, storage, and replay. So, as you can see, this is a very important part, the motion data storage. So we make sure that data logs, the angle logs are saved in a database so the user can go to the specific movement he wants and select it and replay the movement in a loop. That's what the industry requires. They need small medium enterprises need to loop the movement again and again in order the factory to work. So this is our system architecture. Let's move on to the results. So by looking at these results, the system achieves real-time performance with average latency of 57 milliseconds and approximately 10 frames per second. Kalman filtering reduced motion noise by over 40% across all joints. Additionally, the system maintains less than 4 degrees of angular variation, ensuring smooth and stable motion. So you guys can see from this table, these are the raw values we got, and these are the filtered values. So these filtered values are coming from the Kalman filter. We are making sure the movements are smooth. So you guys can see the percentage which the filter filtered. 42% in shoulder motor, 40.7% in the elbow motor, 41.3% in the wrist shoulder, and 42.2% in the gripper motor. And this is the pre-stage processing time. So it takes us 62 milliseconds to estimate the post of the human demonstrator, and to transmit the signals to Wi-Fi, it takes us 57.3 milliseconds. And to compute the angles, it takes us 5 milliseconds. And to filter out the angles through Kalman vision, it takes us 2 milliseconds. So these are the results and performance metrics of our project. So in conclusion, this work presents a real-time vision-based human-robot interaction system. It enables robots to learn directly from human demonstration without any complex programming or key inverse kinematics. The system achieves smooth motion using Kalman filtering and runs entirely on raw-cost embedded hardware. This makes sure robotics are more accessible for small medium enterprises. Not only small medium enterprises, education institutes, and real world applications as well. So we make sure that it doesn't require any high cost GPU. So every small medium enterprises, every startup can use this robotic arm to make the system to make their business a successful business. So that's it. If you guys have any questions, you can ask. This is my contact information. You can contact me through this media, and I will be very happy to answer your questions. Thank you.
Thank you. Thank you. We appreciate it, Anjanadip. Floor is open for questions. Thank you so much. Thank you. Do we have any representation from paper 274, please? Okay. Sandeep, are you online?
Yes, I am.
Yeah, thank you, Sandeep. So we do not have a representation from paper ID 274. I believe we can wait for 3 more minutes and we'll see if they can still show up. Okay, that concludes I believe, our final presentation for this session. Sandeep and I would like to extend our sincere thanks to all our speakers. You really brought in some experimental studies and insightful thoughts. Thank you for your participation, and I would like to request everyone to join me in a round of applause for all our presenters today. Thank you so much. Thank you. Yeah, we conclude this session, and Sandeep, if you can stay back, I would want to share some insights with you. All right, with this, we conclude this session. Sandeep, I think I'll try to call you directly. I think that concludes our session. Thank you so much once again. We are closing this session right now.